welcome to the course on FPGA based signal processing systems. As a part of sequential circuits, we will be doing the finite state machines in this lecture. The state machine block diagram, which is given over here, the input of the state machine, which is X. Okay, so the output of the state machine is Z. Okay. So this contains the state machines of the digital circuits contain the three major blocks, which would be the state memory, which is a very important block of the state machine, which takes, of course, the clock also into consideration, apart from the excitation signal which comes from the next state logic. So the next block diagram is of the state machine is next state logic, which is also called the excitation logic, which gives the input to the state memory, which decides the excitation to the state memory. Of course, the state memory contains the flip-flops in the digital circuits, and the next third block, major block, is the output logic. So the output logic, which is deciding the output from the state memory and the input as well, are only the output from the state memory. So there are two based on this output from the state memory, which decides the output logic. We can classify these state machines into two categories, like Mealy and Moore machines. So this is usually called the excitation signal, S next, and this is the current state of the state machine. So the number of states depends on the number of flip-flops you use. If you have using the 2 flip-flops, then that states would be restricted to the 4. We have 3 flip-flops, again 2 power 3, this again can go up to 8 states. So the current state, and if the state machine decides the output, this is based on only the current state, that is this portion. Anyway, the current state also gets into the next state input. So the input and the current state decides the next state. What should be the next state? This is often a combinational circuit. This is a combinational circuit. Similarly, the output logic is also a combinational logic circuits. So this combinational logic, so the current state decides the output, then we call it as Moore state machine. If the current state and the input, also the other line, decides the output logic, then we call this state machine as Mealy machine. So Moore and Mealy state machines we'll do in this lecture, and the codes, Verilog modules for the development of the state machines also. So the major 3 blocks needs to be considered in the kept in mind. So each of them we should have a Verilog module, actually the module or a single module which contains these 3 parts, state memory, and then the next state logic and output logic. So in this case, the input, which is X, which can be an enable to the next state logic, or it can be an enable input to the output logic as well. So it can even decide based on the input required. So the input the input which directly connects the output logic plays a different state, gives this different state machine, that is a Mealy one. So now getting into the state, suppose given a logic diagram, the digital logic circuit, in that for example, if we have the input here, which may be an enable also, and we have this Y output. Okay. So here the input and the output Y. So we can see there are combinational circuit here. There are enable is complemented, and the Q naught, which is feeding back to the certain gates here, and for example this gates, and we have some NAND gates over here. and the NAND gate outputs are clearly getting into the flip-flops, two flip-flops. So and the output of the flip-flops are going into the AND gate where there is a, so this is the output logic. Only the outputs of the state memory this state memory is getting into and logic. Also the input from the circuit also is connected to the and logic. So it's if you design this behavior, then it will be a Mealy state machine. And you can see the block box which is giving the state memory, and the block Q over here gives the next state logic. You can call F and G or any name. So this is the next state logic. So the feedback also could be observed from this Q naught and Q1 is the current state, and so this current state here, and it is fed back here to the next state logic. You can see Q1 is getting in, and then Q naught also is getting in here along with the enable input. So that's giving the next state logic to the D naught and D1. What should be the next state? So because it's connected to the D flip flop, the next state is decided by this here and given to the given as an input, and which gives the output Q naught and Q1. So taking this circuit as an example, and how for a given digital circuit, how do we get the state diagram? Okay, so here, so first we look at the circuit, and so that if we know the state diagram, like what we did in the counter example, if you see it is moving from 00 to 01, 10, 11. So then how that, considering the state diagram, and how do we develop a Verilog module for it? Okay, so we are going to develop the state diagram for this, actually the state machine, and then we'll model that in the Verilog. So the excitation equations first, what is the excitation equation over here? So the D naught and D1 is the output which output of the next state logic, and which is getting into the flip-flops. So the D naught and D1 we can represent here as, so if we take this point, this is Q naught dash and enable Q naught dash here in this NAND gate, and this is NAND, and over here enable dash and then Q naught and then NAND, and those two are again given to a NAND gate here. Okay, so D naught is this. So we get the output Q naught En dash and then Q naught dash En and R. So it's an invert R function also. NAND function is equal to the invert R. If we apply the De Morgan's law, you will be ending up with the D naught. Also this Dn, this equation here again giving the enable dash and the Q1, enable dash and Q1, the first one, and the second one is Q1 dash and then enable and then Q naught dash also here we have this take, and then another one also the Q1 and Q naught dash and then it goes to the enable. So three of these expressions and NAND them, and then further three expressions AND function and then complement. So NAND function gets this equation. So first decide this D naught and D1. It is based on the input enable is, and it is based on the feedback from the Q naught and Q1, which is the current state. So Q naught, Q1 are the current states here. So once we obtain, this is the first step to obtain for the given digital circuit, get the excitation equation, and then get into the characteristic equation. So characteristic equation is that what is the D flip flop we will be using. So it may be a T flip flop or a JK flip flop or whatever. Here we have used this D flip flop, and whose characteristic equation, that is Q naught here and Q1. The next state of this Q naught star and Q1 star, it's simply D naught and D1. So it is going to be D naught and D1. So we can get it from the functional table also of the T flip-flop. So, for T flip-flop this characteristic equation would differ, and for JK as well as the characteristic equation, whatever the flip depends on the flip-flop, this characteristic equation would differ. So, these are the first two steps after obtaining this Q0 star and Q1 star, and will give to the transition equation. So, the transition equation where we know this Q0 star and Q1 star, which is here, and D0 and D1 obtained. So, the D0 from this expression substitute over here. So, that is what they get here, that is the transition equation. So, getting Q0 and Q1, maybe we can get it directly also. So, it is better to do it in parts, so to avoid the mistakes. So, D0 is from this expression substitute over here, and D1 from this expression substitute over here. So, you get this transition equations. So, that is the third step. Get the excitation equation and then characteristic equation, and then the transition equations. What is that Q0 next state and Q1 next, and then output Y, that is this output Y is here given an AND gate, simply the output logic Y equal to enable into Q0 and Q1. So, this is the Q0 star and Q1 star. So, whereas in case of suppose there is this enable input is not available, suppose this line is not there, then the output would be Y equal to Q0 star and Q1 star only. So, that makes the difference here. In the case of Mealy machine, we have the enable, and whereas in case of Moore machine, only current states decides the output. In case of Mealy machine, current state and the input decides the output. So, this is the output equation for the Mealy and Moore. So, we have this 4 steps done. So, from this 4 steps, we will be making certain tables to get the state transition diagram. So, here is for the Mealy machine, what we have this first, that Q1 and Q, because there are 2 flip-flop outputs, Q0 and Q1. Suppose this can take a combination of 0 0 0 1 1 0 1 1. In that case, enable, that is the input, enable input, if this is 0, what happens to Q1 and Q0? Okay, so this Q1 and Q0 here is used to this equation here. So, enable 0, this becomes 1, and Q0 is 0. And this is 0, and here Q0 is 0, so this becomes 1, and enable is 0, so this becomes 0. So, similarly Q1 star is computed. So, here when enable is 0, what is Q1 star and Q0 star? So, assigning these are the combinations. Suppose we have the 3 flip-flops, then you will have 8 states over here, and enable 0, what are the Q0 star and Q1 star, and enable 1, how this Q0 star and Q1 star changes. Okay, so similarly for enable 0, when Q1 and Q0 are 0 and 1, what should be the Q0 star and Q1 star? So, in this equation, so Q0 and Q1 are 0 1, and enable is 0, enable is 1. These 2 conditions, what should be the output? So, we get this states, different states for different combinations. So, we call this as present state, and this is going to be the next state. Okay, so 0 0 will be the next table. This is this enable 0 and enable 1. So, what we do is then we call this Q1 and Q0 as state. Yes, so, and name some alphabets like A equal to 0 0 is A, and 0 1 is B, and 1 0 is C, and D is 1 1. So, from enable, and then similarly if it is 0 0, that replace this next state as this 0, this was 0 1. So, 0 1 and 1 0 1 0 1 1 1 1 and 0 0. So, we can even you choose any of this, the alphabets may be anything, PQRST, any of this, or PQRS, or any alphabets for this, just a representation of these states over here. So, this is the next state which is given over in this first and second, this column and this column. So, this is present state, and S is the present state, and then S star is the next state. So now the Mealy, if Mealy machine usually decides that also the outputs. So the output, we have this enable output equation Q naught star and Q1 star. So when enable is 0 and Q naught this a value, Q naught and Q1 star this value a 0, then what should be the output? It gives output. So this is the next state and correspond the output here, and B and output C D0 DA1. So the outputs are mentioned also along with the next states. Okay. So this is for the Mealy machine. So only this output decides this, whether it is Mealy or Moore. So Y is taking into consideration the enable also. So, and the Moore machine, here we have this. So the Y is simply Q naught Q1. So if this is 0, then this is going to be 0. This output here a 0, then it is going to be 0, B is 1, and this is going to be 0 again, 1 because an AND logic, 1 and this is 1 D is 1 we assigned. So this output is 1. So it's not with respect in the next states. So 0, 1, the outputs are not defined along with the outputs in the next states. You can see the difference over here. So that is S star. So this is for the Moore state machine. So now taking this Moore table, and how do we draw the state diagram for this? Okay. Now if we take this, consider this states A, one correspond, draw it with a circle. The states are represented with a circle. So A, and inside the circle the Moore machine mentions what is the state, okay, that present state, current state A, and Y equal to 0, that is this output, and B the next one and 0, and then C the output is 0 over here, D and the output is 1. And then we'll see the transitions. Now what happens when enable is 0, the present state is A, and then what would be the next state? Okay, so the enable is 0, it stays over there. So it is staying over there. The marking, just say we say whether input is 0 or 1. Okay, the output is represented over here in the current state, and enable 1, and enable is 1. This is the state, and enable is 1. So going to B. So from A to B. Okay, the transition is shown over here. So from A to B, this transition is shown over here, and the present state is B now, and then if enable is 0, it stays over there. B equal again B. This is enable 0. If you get enable 1, then move to C. Okay, and if, at the current state C or the present state C, and enable is 0, stays over there. Or move to D when enable is 1. So move to D here, there. Okay, and at D, if enable is 0, stays over D, and if this there is 1, then go to the next state, that is A. Okay, so the enable ones we can represent it with along this transitions. Okay, so this is giving the output along with the current state here, Y equal to 0. The what is A, B, C, D, that what are the current states. This is for the Moore machine. And if we take the Mealy machine, the table, it is shown along with the next state. Okay, next state and its output. Okay, so because enable is also a part of the output. Here given this A, B, C, D, the representation, it's not the output is not represented with the current states. Okay, and the here the representation is that's a different. This, if this is present state, enable is 0, next state is A, and output is also 0. So this enable 0 and output 0 are represented over here. This is input and output. Okay, input slash output. If the enable is 1, go to the next state, that is B. This is the transition line. This is input 1, enable 1, and output is 0 still. So this is the output which is shown over here. And then at B, it stays over there. Input is 0, output is also 0. here enable is 0. If enable is 1, go to C and still the output is 0, it is not done yet. C, at C the input enable 0, makes this stays over there, or move to D when enable is 1, this is, and still the at D again enable is 0, stays over here 0 0, and enable is 1, yes, go, the output is 1, it's done, and it goes to the next state A. So this is the representation of this between the Moore and Mealy machine. The difference, you can see that enable input, which is considering the output as well. Okay, so not only the states, the current states of the, as in the case of Moore machine. So the difference can be observed from this Moore and Mealy machine. So if with a given synchronous sequential digital circuits, how do we obtain the state diagram? The one which we had here are the state diagrams of so these state machines. We have this excitation equation. First identify the excitation equation, or in the given circuit what is the next state logic, state memory and output logic, and identify the state equation, the excitation equations, and then get the characteristic equation of the flip-flop, then transition equation for the current state, deciding the current state with all this excitation equation and the characteristic equation, and get the output equations. So the output equation can be of two types, and obtain the table, state transition table, assign the states some alphabets, and then draw the state diagram. So the state diagram may even contain not the alphabets, it can have the 0 even in the 0 ones also. So this is to give them just the same way. If a state diagram is given, can I get the digital circuit for it? So Verilog modules can be developed in two ways: for digital circuit as such by instantiating all of them, or considering the state machine of that digital circuit. Okay, synchronous sequential circuit clocked one should have the privilege to do the state machine in terms of state machine. So let us see this. So Verilog state machine modeling styles. So first we have this three of them as state memory and the next state logic and output logic. So in that there are three ways. The three important blocks in a module can be done in different styles. Actually, the different styles are the style one, say always with the state memory separately, all next state logic separately, output logic separately. That means in one module we can have three always blocks separately: state memory, next state logic and output logic, and in or we can combine all of them. Okay, state memory, next state logic, output logic. In style 4 we combine all of them in only one always block. Can we have all the three models? Okay, so state memory, next state logic and output logic, all codes in one always block. That is the fourth style 4. Here you can have the style 2 combining state memory and next state logic, okay, and output logic separately in another always block. Okay, or we can have state memory alone in one always block and combine this next state logic and output logic. These two are combinational logic, so it is also can be combined. Or we can combine the state memory and output logic and keep the next state logic separately. So this is the fifth style. So there are various ways in which that state machine modules can be developed using the Verilog. So we'll see one maybe in the coming lectures, each one. So the first module which we have this taking the Moore machine in that. So for the current state, output, and when enable is 0, it is staying over in that state, or it is moving to the next state, and so on. So module, we take the code of this module, which is state machine SM, a module name given state machine. What are all the inputs for this module? So we have this enable or X, the 1, we said enable, and of course the clock to the state memory. If you recall that the diagram what we had, in that state memory needs a clock. So, clock, enable are the two inputs, and then output of the state, the output logic, and the sreg, which is the current state. The sreg is the output. So, we take the output and the current state, are just to check this whether it is moving, the sreg current state is moving from one to another. Okay. So, this is the module description, and then comes the declaration. So, declaration Z is, we are going to Z we will be using always block, and then sreg, that is the current state, and there is S next, which is the next state. That means it is the output of the next state logic. Okay, that is a next state logic which is getting, which is the input to the D flip flops. Okay, the flip flops. So, range 2 bits these are, because D0 and D1 we have, and S is the current state also 2 bits, A, B, C, D are 2 bits here. So, the current state and next state, and we can't have this in the design, we have represented with alphabets. So, instead of this, alphabets needs to be replaced with binary values here. So, the parameter, so use the parameter to define these states. What is A here? A is 0 0. So, you can see that how the parameter declaration helps in defining the states. That is 2 bit 0 0 is A, okay, that is 2 bit 0 1, and comma, the definition does not end, 0 1 is B, that is B, and C it is 1 0, 2 bit, and D is 1 1. So, then semicolon. So, all of them are defined now. A, B, C, D are 4 states. If you have multiple states or 8 states, and you can put all of them in the parameter declaration. So, this is defined states. After that comes the here we have to define the state memory and then next state logic. Anyway, state memory is create the state memory, the first one, always at passage of the clock. Here passage of the clock, assign this next state to sreg, that is the current state. So, we take the state memory block, and the clock, the sreg is S next is the input to the state memory block, and sreg is the output of the state memory block. So, the next state, or the excitation, from the excitation equation what we get is that D0 D1 is given to the current state here. sreg is the current state. So, always at next to making the next state logic. So, in the next state logic, always at the rate enable or sreg. Okay. If you take the if you just recall that the block diagram again, in the input are x and sreg, which is the current state feedback from the current state gets into in the next state logic. So, always at the rate enable or sreg, the two of the inputs are in the sensitivity list. Okay. Enable or sreg, what is the code needs to be written. So, here we use the case statement. So, enable or sreg, where the what's the transition should be happening. So, from the diagram, if you say case if sreg, that is the current state, okay, the current state in the Moore machine, if it is A here, okay, that is sreg, and if we are here, if enable is 0, next state is A, if enable is 1, next state is B. Okay. So, this is deciding the next state logic. So, here if enable is 0, S next is A, S next is simply equal to A. You see the blocking assignments equal to A, else next state will be B. Okay, that is the case A. Okay, this is using the case statement, simple. And next case statement is B, where if enable is 0, stay over there, S next is B, or it is going to be S next equal to C. Okay, that is from the this sreg, always this is the current state, and the next we need to give the C, which is if enable the state, the choice is C. If enable is 0, S next stay over there, otherwise move to S next D, and if enable is 0, S next, else S next is A. Okay. So with this, default needs to be, with the case statement, default needs to be given S next, make it A, or any of this default state is wherever it is. If there is, then the state should come to 0 0. End case, and end with the begin which is over here. We had this begin, so this would complete after for the next state logic, end here. Okay, so this is the end. After we have created the state memory, which is simply assigning this S next to the S rich, and we have from the table what we obtained, that the current state and what is the next state, using the case statement, always using the always block, it's assigned. And then finally the third block, always block, is output logic. So I have used two always block, and here is the third always block, which is the style one. Here 3 different always block, S rich in this output logic. Okay. It is in the Moore machine, if you recall, that output logic is taking only the current state, that is S rich. In case of Mealy machine, yes, this would change enable comma S rich. Okay, so that's the difference in the Verilog model. So case S rich case statement can used A, B, C, the 3 of them in the table, it is 0, the Z output is 0. So for 3 choices A, B, comma C, the output is 0. If D, then Z equal to 1, that is over. So then default, you need to specify Z equal to 0, and then here end case. So this end case gives the complete this code with the end module. Okay, so then the after this completion of this code, that is for always block, with the 3 always block of next state logic, output logic, and state memory. So you get into the test bench where SM, that is TB, that is module name you have given. The test bench inputs are clock and enable. Also output Z and S reg have taken the output. The other one, the next step is to instantiate the module in the test bench. So we had this clock enable Z and S reg. So from this initial begin, initialize this clock 0 and enable 0. Also end, we have the stimulus. Now add the stimulus. This is to plot them, clock, enable, and Z and S reg. So as usual, we do into the test bench of every code. Then enable, make it 0, and then enable is 0. So enable 1 and 0, 1. So initially it is 0, and then 1, hash 50, make it 1, and then hash 200 enable 0, and then 400 enable 1. So when enable is 1 in the state machine, it moves from the one state to another. When enable is 0, it stays over in that particular state, which is from the circuit. So we need a clock, so clock needs to be generated always, hash 50 clock equal to not clock, which is 100 nanoseconds here, the clock. So from this, the output which we have here is the clock edge. We can clock edge, and the enable is 1 over here. So early 50 here, and Z is made 0. Okay, Z is 0. And what is the S reg? That is here. It is first getting into the first state, that is 0 0. Okay, so at first clock edge, when enable is 1, okay, then this is the starting of 0, and then it is already we made that 0. So here next one, that is 0 0, this is the first state A, and then enable is still 1 over here. So this is going to 1, the next state. So enable is 1 over here until this point. Okay, so at this point, this enable is made 0. Okay, so it is staying in that same 1 for a while till that enable becomes 1 over here. Enable is 1 at this point. Okay, so again, so in that state, that is, this is in the 0 0 state, and again 0 1 state. Because of enable 1, it moved to the 0 1 state, and then the 0, because the enable was 0, it is staying in that state only. After that, it is made 1 0, that is moving to the next state. Enable is 1 over all this period, and this is 1 1. After that, again it moves to 0 0 0 0 1, and if enable is 1. But if we look at the Z, the output of the output logic, which is 0, and then only at this point when it is moving to third state, that is 1 1 state D, where the output is 1. Okay, so output is 1. We can see the output over here. So the time we have got the log file also. So initially it is 0, and then it is stay in the 0 1 state for a long time because of enable 0, and then it moves to 1 0 1 1, and then 0 0 1 1. Okay, so Z is only 1 at this point state, that is 3. Okay, and 0 0 and so on. This is the output of that Moore machine what we had, which is moving from one state to another when enable is 1, and stays over in that state if it is 0, same state. Okay, so here the Moore machine, which we had same Moore machine, which can be that style 3, combining the two always blocks. So over here the ridge declarations, everything is done. Only the change what we had is that define the states as such, always at passage of the clock, create the memory, that is separate always block. Yes, and then in the case of next state logic, which is taking enable and the sreg, we have the current state and the input, both are given to this, and giving the case statement. Similarly, if enable, it is similar to the previous code which we had C and D. After this, we have only the change default case, end case. Then you can notice the change would like to say this always next state logic, the output logic is brought into the next state logic, combining in the style 3. So if sreg is A in state A, Z equal to 0. Okay, so if you remember in the previous example, we have done it in the separate always block. Separate always block gives the output logic in which the sreg is the case statement is used. Case A, B, C is Z equal to 0, other case D is 1. Okay, so here if case A is at 0, else if it is case B, that is this is sreg is B, then is at 0, or else if sreg is C, is also else if Z is 0, and else they make this is at 0. So you can use the priority structure as well in the state A, B, C, D here. If so, the end. So we have combined in this example, we have combined this next state logic and the output logic. The output logic is with if else statements in one always block, and the state memory is retained as such in a separate always block, always at the rate of passage of the clock. Yes, next is assigned to sreg. Okay. So here the difference, I mean the code is only having always two always blocks only. Okay, to simplify this, this is one model in one style of coding which next state logic and the output logic can be combined, because these two are combinational circuits. Okay, it's easy to combine them using the blocking assignments. So else if this is the one. So we'll see the test bench. The test bench is that module, and then we have the instantiation of the module sreg and clock, enable Z and sreg, all of them. Also they initialize them that, and then give the stimulus, the same stimulus what we had given earlier. So now the clock. We'll see the output. It would be the same output. There is no difference in the output, but we want to see the style of coding, how we can, the coding style can be changed. So over here, when it is getting into the initial state 0 0, and then it goes to 1, and because of it is 0, enable is 1, it moved to first state. After that, enable 0, so it is staying over there, and enable is 1 2 3 and is moving. At this state it gives 1. So the same output what we have got in the previous case also. The style of the coding is, we have brought the if-else statements or the output logic into the next state logic, and in the first example we took the case statement for output logic, and in the second one took the if-else statement for the output logic, which is put inside the always block of the next state logic. So this is style 3, that is combining them. So state over the states can be seen over here as well, 1 0 1 1, and then it moves 0 0 0 1 as also. So what we had done, we have a state machine, how the state machine, what are the different types of state machines, like Mealy State-machine and the Moore State-machine. So how this is, how the current state decides the output in the Moore machine, and in the case of Mealy machine, current state and the input logic decides the output. Also, if we take the state machine itself, it is having the 3 important blocks: state memory, next state logic, and output logic. For a given digital circuits, a sequential, synchronous sequential circuit, then it is easy to have the 3 parts separated, and we can have the Verilog module developed in either it is in a Moore machine or Mealy machine. In the next few lectures, we'll have the Mealy machine, and then we would also, if a given circuit we got the state diagram, if the state diagram is there, can we get this digital circuits also. Those things we will be dealing in the next few lectures. Thank you.